In May 1976, a DC-10 jetliner equipped with a rudder section made from a graphite epoxy composite was undergoing taxi tests at Long Beach, California. The upper aft section of this four-segment articulated rudder was the result of a contract awarded to the Douglas Aircraft Company by NASA's Langley Research Center. The contract included the design, fabrication, certification, and flight service evaluation of a graphite epoxy structural component. This film documents the efforts of the contract. In January 1974, the contractual effort began. It soon came to be known as the DC-10 Graphite Epoxy Rudder. Early in 1974, during the preliminary design phase of the contract, 7 design concepts were evaluated. At first, interest centered on honeycomb-type configurations because of their fully stabilized skins, relatively few detail parts, and established assembly techniques. However, as the design studies progressed, interest focused on other structural arrangements, including the rib-stiffened skin design that was finally selected. This interest was based on the successful laboratory production of graphite epoxy parts using a unique new fabrication approach, the thermal expansion molding technique. The selected design consisted of a graphite epoxy box structure with standard aluminum alloy hinge fittings at the 5 hinge stations. Leading and trailing edges and tip were of fiberglass epoxy material. A metallic lightning protection system was also incorporated. The rib-stiffened skin design was selected after a number of detailed studies on relative weights, fabrication costs, tooling requirements, and number of manufacturing operations. Preliminary tooling and manufacturing plans indicated that the rib-stiffened rudder could be fabricated in a one-step manufacturing process, one that eliminated repeated handling and secondary bonding of detail parts during fabrication and sub-assembly steps. At the heart of the one-step rudder manufacturing operation was the large thermal expansion coefficient of silicone rubber. Also, silicone rubber could be readily fabricated into internal mold elements or mandrels. Used in an oven-heated form mold die, the rubber mandrels provided the pressure required to consolidate the individual B-stage rudder parts into a cured monolithic laminate assembly. To establish the feasibility of this manufacturing approach, 8 development components were produced using a specially developed form mold die. Problems encountered during fabrication of the components were gradually resolved by redesign of metal and rubber mandrels and adjustments in curing temperatures. Rudder skin panels consisted of span-wise and 45-degree oriented plies in a 6-ply pattern. The skin panels, spars, and ribs were hand-laid up from uncured graphite epoxy pre-preg tape. Fore and aft boundaries and the upper edges of the skins were reinforced with the quasi-isotropic pattern to permit attachment of the leading and trailing edges, the tip assembly, and the hinge and actuator fittings. With the design and the manufacturing process selected, work began on the fabrication of rudder component test articles. A forward spar test component was assembled using accurate form blocks for placement of the spar web stiffeners. Following layup, the test structure was oven cured at 350 degrees Fahrenheit. Static testing of the spar was performed to verify design details in the area of the hinge and actuator fittings. To simulate spar loadings, two different test setups were employed. One was at the lower hinge station where a 78% positive margin of safety was recorded. The second, at the center hinge station, indicated a safety margin of 140%. In each case, the spar specimen failed in the expected shear mode through a circular cutout in the shear web. Another development component tested the hinge fitting fastener to verify its fatigue strength. At the critical attach points of the rudder actuator fittings, a simplified but conservative fatigue load spectrum was applied. Minor failures were experienced with fastening screw heads, as well as some secondary debonding and delaminating outside of the test section. After repair, the specimen successfully withstood 3 lifetimes of fatigue loads. Later, a residual static strength test indicated a positive safety margin of 96%. The rudder development phase began with the fabrication of the full-scale form mold die tooling. Development continued with the manufacture of 4 full-scale prototype rudders. One-step manufacture of the graphite epoxy structural box was accomplished by means of the form mold die. During this period, processing problems were systematically eliminated. A 3-foot-long rudder box test component, consisting of the upper 8 rib bays of a prototype rudder, was subjected to vibration testing. The component, equipped with standard push rods and attaching hardware, was mounted on a shaker unit for random vibration test runs ranging from 350 to 1800 hertz, simulating typical in-service rudder conditions. In all, nearly 47 hours of vibration testing was performed until endurance limit stress cycles were accumulated. At the end of 100 million stress cycles, there was no significant component damage. Static load tests were conducted on a second rudder box component, also taken from a prototype rudder, to verify the strength and fail-safe capability of the hinge and actuator fitting attachments. Concurrently, the skin panel stability and the strength of the rear spar flange were verified. The component used in these tests consisted of the 9 lower rib bays of the rudder, along with the lower hinge and actuator fittings. The test loads, selected to verify design concepts, were successfully sustained in all 7 tests. The last test was conducted with a whiffle tree loading fixture to determine rib strength and was a prelude to the upcoming static tests of the full-scale rudder. The 4th full-scale prototype rudder was selected for ground testing to obtain data required for certification by the Federal Aviation Administration. For this final prototype rudder, the total cure time was 12 hours, 6 hours for heat up at about 1 degree Fahrenheit per minute, 2 hours at 350 degrees Fahrenheit, and 4 hours for cool down. Following the cure cycle, the prototype rudder box was non-destructively tested using ultrasonic inspection. A liquid coupling agent was first applied to rudder surfaces. This assured better contact between the probe and the surface of the structure as the operator traced the junctions of the internal structure and the skin panels. The cathode ray screen displays indicated that a quality component had been produced. The static test program on the graphite composite rudder simulated critical flight loads, including those induced from forward rudder bending and applied air loads. Simulated air loads were generated by a hydraulic actuator acting through a compression whiffletree system to 71 load points on the surface of the rudder. 9 tests were made, including all well and fail-safe configurations with either hinge or pushrod bolts omitted, without a structural failure of any kind. The 10th and final test duplicated one of the all-well load conditions. The applied loads were increased above ultimate in an effort to determine the failure load and mode. At 415% design limit load, the test was suspended prior to failure of the structure because the compression whiffletree system was nearing critical buckling conditions. With the successful completion of the static tests, the manufacture of 10 flight service graphite epoxy rudders began. Manufacturing data acquired during this phase of the contract indicated that recurring direct labor for each succeeding unit declined from 2,542 man-hours for the first rudder to 1,889 man-hours for the 10th unit. Operations requiring relatively high recurring labor costs were machined parts fabrication, graphite epoxy composite hand layup, and rudder final assembly. Installation of the 5-ply fiberglass epoxy leading edge, trailing edge, and tip structures constituted the final stage of graphite epoxy rudder manufacture. The 12-segment leading edge structure, similar to its conventional metal counterpart, was attached with flush screws and nut strips and nut plates to the rudder box. The 3-segment trailing edge was an adaptation of the existing DC-10 design to the graphite rudder box geometry. It was attached to the rudder box structure with a cold set adhesive in addition to the attach rivets in accordance with previously established transport aircraft design practices. The tip assembly was riveted directly to the upper closing rib of the rudder box. In these final assembly operations, direct labor recurring man-hours for the 10 composite rudders decreased from 408 man-hours for the first rudder to 257 man-hours for the final rudder. The ground testing required for FAA certification was completed with the laboratory modal vibration survey tests on the first flight service rudder. For these tests, the upper aft graphite epoxy rudder was assembled with a metal upper forward rudder that had hinges modified to accommodate differential thermal expansions between the 2 structures. The test setup was completed with standard DC-10 push rods, hinges, brackets, and attaching hardware. Resonant frequencies and mode shapes were determined for the basic design, as well as for 6 fail-safe conditions involving hinge bolts or pushrod failures. Flutter evaluations performed in accordance with FAA regulations indicated that flutter speeds of the DC-10 with the graphite epoxy rudder were equal or greater than those with the standard metal rudder in all modes tested. Following painting, the first graphite epoxy flight service rudder was installed on a DC-10 airliner in April 1976, a prelude to the first flight of the graphite epoxy rudder on an experimental basis. After receiving FAA certification for commercial airline service in May, Douglas installed a second flight service graphite rudder on a Western Airlines DC-10. A month later, the composite rudder entered passenger carrying service with Western Airlines. The 5-year flight service period for the graphite epoxy structure had begun. During the next half-decade, commercial flight experience with the composite rudder will be reported by Douglas on an annual basis. The flight service phase of the program had made a smooth and uneventful start. The 2-year program had already achieved its primary goals. An advanced composite rudder section for a commercial jetliner had been designed and developed, and it had been successfully manufactured using a unique one-step manufacturing process. Extensive manufacturing cost data had been acquired, indicating that further reductions in labor expenditures should be sought through fuller exploitation of low-cost manufacturing operations. Ground testing had proved that the structural strength of the DC-10 graphite epoxy rudder exceeded design requirements by substantial margins. The composite rudder weighed 33% less than its conventional metal counterpart. In all, it was a program that did much to advance the practical application of advanced composite structures technology, a field holding high promise in the production of the stronger but lighter aerospace vehicles of the future. In May 1976, a DC-10 jetliner equipped with a rudder section made from a graphite epoxy composite was undergoing taxi tests at Long Beach, California. The upper aft section of this four-segment articulated rudder was the result of a contract awarded to the Douglas Aircraft Company by NASA's Langley Research Center. The contract included the design, fabrication, certification, and flight service evaluation of a graphite epoxy structural component. This film documents the efforts of the contract. In January 1974, the contractual effort began. However, as the design studies progressed, interest focused on other structural arrangements, including the rib-stiffened skin design that was finally selected. This interest was based on the successful laboratory production of graphite epoxy parts using a unique new fabrication approach, the thermal expansion molding technique. The selected design, it soon came to be known as the DC-10 Graphite Epoxy Rudder. Early in 1974, during the preliminary design phase of the contract, 7 design concepts were evaluated. At first, interest centered on honeycomb-type configurations because of their fully stabilized skins, relatively few detail parts, and established assembly techniques.